Okay, let's get started, please. So today we're going to go backwards to chapter 3, which is sequences, and eventually series. Once we can start adding things. You've probably seen sequences in calculus before, but this time we're going to be doing sequences in metric spaces. So just more general. So you have a function going from the natural numbers into a metric space. Okay, so that's your sequence, right? To every number, it's going to associate a point, right? So like 1, 2, 3, 4, 5, etc. And then there's some space over here, right? And then to every value, it associates a point, and that's your sequence, right? So this you have a sequence given a function from n into x, a metric space. In other words, a sequence in x. We say that the sequence converges. So let me say it this way: if there exists a point p in x such that roughly speaking, the sequence tends inexorably towards that point. Okay, but that's just English, right? That's not the definition. Yes. So if there's a point over here, and it has this property that if there's a point with the property that no matter what epsilon neighborhood around it is given, there exists a time past which all p sub n lie in that neighborhood. Okay. If there is such a point with that property, then we say that the limit of p sub n is p as n tends towards infinity. That the sequence converges to p. Okay, so that's the definition. Okay, so that's the formal definition, and the way you want to think about it, right? The image that this corresponds to is that here's this. If there's a point P, and no matter what neighborhood you take, there is a point past which everybody lies inside there, right? So here's this neighborhood, and maybe it's at point 1,000. Everything past 1,000 goes inside, gets mapped inside there, and so no matter what neighborhood you give, there's a corresponding time past which everybody stays inside, then that's called convergence. Why?
So I mean, maybe I'm mixing things up a little, or I think I am a little bit, but like with the neighborhood, like, because like assuming like with our definition of like continuity, like the topological definition, does that pre-image of that neighborhood have to be like open in the?
Yeah. So that's a really great question. So like, what does that say? That says that. That says you can think. So yeah, what you're asking for is kind of like the metric space version of this. And so the way you want to think of it is like, let's see. Let me draw it like this. So over here you have some epsilon neighborhood, and what do you have over here? What you have over here is an open set like this. Okay, so this is like your delta neighborhood. This is like, here's the epsilon neighborhood, and then you're wondering what's the delta neighborhood? The delta neighborhood is this thing here. Okay, the delta neighborhood is this thing here. It's rather the n infinity neighborhood. It's a neighborhood of infinity is what it is. Okay, so it's like if you want, you can call it like an n neighborhood of infinity. Right? So given any epsilon neighborhood over here, there's a neighborhood of infinity in which all the points in here get mapped inside there. It's exactly, that's a very good way of thinking about it. Okay, so yeah, we could write it just that way. So like for all, epsilon neighborhoods of P, there exists a neighborhood of n infinity such that P of n infinity lies inside of the epsilon neighborhood of P. Right? If you like metric spaces, and you may. Right. Okay. Okay. Let me make two kind of minor comments. One is that convergence depends on the metric. Right? Because points that converge in one metric don't necessarily converge with respect to the other metric. Right? Getting close in one metric doesn't mean anything about converging, getting close in another metric. So depends on the metric. Two, right? So you can have the same space, but with a different metric, you may not have the convergence may not hold. Two, convergence. If there is no point, if there is no such point, P and X, then we don't call it convergent. So, for example, like if I had P sub n defined as 1 over n, n from 1 to infinity, right? Then that's going to converge with a regular metric. That's going to converge to 0, right? But if I think of this P as going from n to 0 infinity, then it doesn't converge because there's nothing there for it to converge to. Okay, so it's just a minor point. Like the point has to exist in the space for you to be able to say that it converges to that point. Okay. Okay. So let me just use this one as a simple example, right? So as you know, the limit of these guys is 0 as n goes to infinity, right? As n goes to infinity, 1 over again goes to 0, you know, with the normal metric, right? Right. So let's say that this is 1, right? You've got 1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on and so forth, right? And you know, in order to show this is true, so right, to prove this, right, we must show that you know, given any epsilon neighborhood of 0, right? Given any epsilon neighborhood of 0, there exists a time past which all piece events lie in that epsilon neighborhood of 0. Right, and I've written this in graph, like as a graph, but it probably makes more sense to write it as a map. Right, so here's n. Here's n, right, and then here's r. And let's say this is 0, and this is 1. Right, of course, 1 goes to 1, 2 goes to 1/2, you know, 3 goes to 1/3, 4 goes to 1/4, 5 goes to 1/5, and so on and so forth. Right. So here's piece of 1, piece of 2, piece of 3, piece of 4, piece of 5. Right, and this is the point. This is the limit. Right, and what we have to show that the convergence is, you know, that these guys converge to 0, means that we have to take, whenever you take a neighborhood of 0, there's some time past which everybody gets mapped into that neighborhood of 0. Okay, and then on the graph, what that corresponds to is something like this, right? Whenever there's a neighborhood of 0, this is, you know, right? Whenever you're looking at a neighborhood of 0 for the outputs, you know, there's a time past which all the values lie between the bars, right? This is, you know, your p plus epsilon, p minus epsilon, right? This thing here is your neighborhood, your epsilon neighborhood of p, right? So you want to have it so that, you know, all the points lie inside the bars, okay, right? So, you know, of course, if I say, like, you know, suppose epsilon is 1/10. Right? Then what's the corresponding n? 11, right? As long as I'm past, you know, as long as I'm at 11 or beyond, you know, all my values are going to lie in the bars here, right? Because they can be, you know, 1/11th, 1/12th, etc., etc. I guess taking n to be 10 is okay, because when I say past which, I mean like n greater than n, and strictly greater than n. Okay. Right? Or if I say, like, you know, suppose I want you to stay within 1,000th of n, 1,000th of 0. Well, taking n to be 1,000 will do that for you. Is that okay? Anybody confused? Rachel, it's okay? Okay. Okay. So suppose I want you to stay. So, you know, if epsilon is 1/10, then taking n to be 10 will do. And anything bigger than that will also do, right? Because if this number works, if everything past this works, then everything past something bigger than that will also work, right? Right? For n equals 1,000, then for epsilon equals 1,000th, taking n to be 1,000 will do, and so on and so forth. And if I take epsilon, just plain old epsilon, then what n will do? Don't shout it out, please. Write down something. What should my n be? Okay, turn to a neighbor and say, n equals blah will do. Did you do this already?
In the sense that, like, I used something similar with that idea on the last. It was the one function with the 1 over n. If rational, 0 if irrational, prove that it's
Okay.
that question.
Okay. Okay. So I hope everybody thinks that 1 over epsilon will do. Certainly. So n equals 1 over epsilon will do. Right? Because you ask yourself, the scratch work, if you wanted to do some scratch work, you'd say, I want n such that n bigger than n ensures that p of n, piece of n lies between epsilon and negative epsilon. Right? And piece of n is 1 over n. Right? So, I want a number so that if I'm bigger than that number, then this thing is smaller than and I know that I don't have to worry about this left side because 1 over n is always bigger than 0. Okay. So I want some number such that n being bigger than it ensures that 1 over n is smaller than this. Right? But this thing over here, we just turn it upside down. This is the same thing as saying that n is bigger than 1 over epsilon. Right? So, as long as n is bigger than 1 over epsilon, n is going to be bigger than 1 over epsilon. Right? So if I take my n to be 1 over epsilon, that'll do it for me. Right? So you do some scratch work, and then you would say, given epsilon greater than 0, let n be bigger than 1 over epsilon. Then, if n is bigger than that big N, which is bigger than 1 over epsilon, little n will be bigger than 1 over epsilon, and thus 1 over n is smaller than epsilon. And so, piece of n does lie in the epsilon neighborhood of 0. Okay. So given any epsilon neighborhood of 0, you found a time past which everybody lies in that epsilon neighborhood of 0. Okay. So I hope people are getting a sense of what it means for a sequence to converge, right? It means that you can play. One way of thinking about it is that you can play the epsilon delta game, right? Here's the epsilon n game. Whatever epsilon is given to you by your opponent, by the adversary, you can respond. You're always able to find an n that will satisfy the opponent. Okay. So. Right. Of course, it roughly means that you're able to make your sequence as close to this value as desired, right? Like I can make it within 1,000th of 0. I can make this thing within 1,000,000th of 0. No matter in terms of tolerance, right? No matter what tolerance about 0 is demanded, there's a neighborhood of infinity in which that tolerance is satisfied. Okay. Okay. So that's convergence, and we have some consequences of convergence that should be pretty straightforward. think you can probably prove them. I'll have you try it. So you have p sub n, a sequence with an x, a metric space. Okay. Various useful properties. P sub n converges to p in x. So we also write it like this with an arrow. P sub n converges to p in x if and only if every neighborhood of P contains almost all of the P sub n. And almost all means all but finitely many. Okay. Every neighborhood of P contains almost all of the P sub n. Okay, so almost all means something very different in mathematics than it does in regular speech. Okay, do you have a question? Somebody have a question? Okay, next. If P sub n converges to P, and P sub n also converges to P prime, then P and P prime must be the same. So there cannot be two separate points that both are the limits. If Pn converges, then the sequence is bounded. And fourth, if E is a subset of X and P is in E prime, then we can construct a sequence E sub n that converges to that point, that limit point. Okay, I want you guys to try these. So let's start with number three. Number one. Yes. I see I've reached that age. we made fun of a professor. He would say like, okay, we've got this manifold M, and then there's There was a professor at Chicago who was notorious for his bad teaching. It was said that he used only two symbols, one of which was an alpha rotated 45 degrees counterclockwise, and the other was a gamma rotated 45 degrees clockwise. Anyway, it was this guy who would get kind of confused between letters, but I cannot mock him anymore. Okay, try number three. Take a minute or so, and you should be able to do this. Take 1 minute, 2 minutes at the most. 1 minute for thinking, 1 minute for talking. Okay, talk to somebody. Turn to somebody nearby and say, yeah.
And just one and all of them.
Found it.
And then if you can, that's just the stuff that's like, if you can do that, then you're bound.
There's only a finite number of points outside of the ball.
Because it's like obviously we know that
You say like
the
that's
big end
all.
onward.
You know, there's a finite end.
Like,
Every
so it's just
end
getting
goes
the,
to
yes.
So that means
There's
it's
only,
points from 0 to
no,
n.
that's true, no, that right, because you're, defining and saying that there's some key, you could be where the
Well, like,
neighborhood
you take
epsilon.
like, let's say like 5.
Like the epsilon is like the,
No,
the
because-
given part. And then
Right.
you're saying
So you're saying that that's enough to say that it's bounded?
Well, yeah, there's only
Like not that all the points have to be, in my mind.
Okay, let's get started. So anybody want to tell me the idea or an idea? Tell me what your idea is. Right? You got these guys. If somebody said, "Is this true at all? If this converges, then the sequence is bounded." Like, how would you sort of like instinctively convince them that that's the case? All right, Izzy.
Okay.
You're semi under the ban.
So after like big N, it's all within the neighborhood of epsilon.
Yeah.
So can you find some epsilon big enough so that big N is just going to be 1 and then it's all within the neighborhood?
Oh. Yeah, that, I mean, you can do it. Yeah, so that's kind of a funny way to do it, but yeah, you could. So let's go with that.
Cool.
Okay, so you say, let's take any old epsilon. Take any epsilon, right? Then, here's your epsilon. And you're saying, well, look, there's going to be some point past which everybody's inside here, right? Everybody's inside here, and then there's just finitely many guys outside, right? And then what you're saying is that now measure the distance to each of those guys, right? Measure the distance to each of those guys, and then take the largest distance and call that epsilon, right? Call that epsilon. Then everybody's inside there. Yeah. So that's yeah. One can do that, and that's basically how one does it. Although yeah, that'll do. So take any epsilon. Then there exists an n such that for all n bigger than n, p sub n, the distance of p sub n from p is smaller than epsilon. Right? Everybody's inside the epsilon neighborhood, past that point. Okay. So now, then take the distance. So the only ones on the outside, only P1 through Pn might be outside this epsilon ball, right? Okay. So let capital D be the max of the distances from P1 to P and Pn to P. Okay, so let that be the max of all the distances.
I have a question.
Yeah.
This is going back to the original definition.
Yeah.
So if we're saying for all there exists an n such that for all n greater, so p sub big N is not included in the epsilon ball.
That's right.
Okay.
Yeah. It doesn't really matter. Like if you said, if we made the definition like this, then it's the difference, this is just a difference of 1.
Right. Okay.
Yeah. But the way that most people do it is for all n greater than capital N. Okay. So in that case, then all pi are in the ball whose radius is the max of epsilon and d. Right. It may be that you chose like a too strong epsilon, a too strong n, and maybe actually everybody lay inside the epsilon ball to begin with. And so maybe your d is smaller than your epsilon, right? So like maybe all these guys who are after n actually lie in an even smaller ball. So I have to say like take the max of epsilon and d just to be safe. Yes, machine.
You can also just go up to big N plus 1, right, to ensure that it's handled.
Well, that big N plus 1 might still be inside. Might still be something smaller, much smaller than epsilon. Yeah. Okay. Okay. In any case, it's bounded, right? Everybody okay? Good. Yeah, this is pretty much how one does the proof normally goes. Okay. Yeah.
I just had a question. Me and Wyatt were discussing this. Is this infinite sequence of points compact?
No, you don't know that, right? It's just a bunch of points in a metric space, right? Yeah. I mean, yeah, no, you don't. I mean, if you knew that we were in Euclidean space, say, and you took the closure of the set of points, then that would be a closed and bounded set, and it would be compact, but not in general. Okay. Okay. Let me do number 2. Just in the sake of, for the sake of time. So Pn goes to P, Pn goes also to P prime, show that P and P prime must be the same thing. This sort of thing you've seen before. You say, well, look, suppose P and P prime are different, right? Suppose P and P prime are different, then, do you wanna do it? No?
Yeah, I'm kind of following along. So.
Okay.
You take like the epsilon, so it's like a third of the distance.
Exactly, yeah. So you say take epsilon to be like a third of the distance between them. You know there's a time past which everybody's inside this ball. You know there's a time past which everybody's inside this ball. But then past the greater of those times, the points must lie in both of the balls. Contradiction. Okay, so I don't know if, take epsilon to be 1/3 of the distance between P and P prime. So suppose P is not equal to P prime. Take epsilon to be a third of the distance, then can find the time such that if you're past that time, then the distance of P sub n to P and the distance of P sub n to P prime are both smaller than 1/3 of the distance from P to P prime. Right? Both of them would be less than that. And that leads to a contradiction, right? Because then then the distance of P to P prime is, by the triangle inequality, smaller than the distance of P to Pn plus the distance of Pn to P prime, which is smaller than 2/3 the distance of P to P prime, right? And so you get 1 is less than 2/3. Yeah.
For this, we also say that Pn is in both balls, but the intersection is empty.
Also works. Yep. Also a contradiction. Yeah, I just wanted to show this one because it's different from that one. Okay. I think I'm not going to do number 4. Let me let you think about. Let's see. So one direction for the first one. So the first one says, if Pn converges to P, then every neighborhood of P contains almost all of the P sub n. Okay. If Pn converges to P, then every neighborhood contains almost all of the P sub n. So the forward direction is straightforward, right? You know, given an epsilon neighborhood of P, you know that there's an n past which everybody lies inside there, right? The only guys who are outside are the finitely many guys between 1 and n. Okay, so that's easy. Let's not do that one. Take a few minutes and prove the reverse direction. What time is it?
1:53.
Really? So by an actual watch. Okay, thank you.
Yeah.
Thank you.
Okay. Well, I guess you could say that there's like a, I think I'm just saying facts, I don't think I'm actually doing anything. But I guess you could say that there's a finite subset in the PNs, which we know is going to correlate to 1 through big N. Don't know what that means. And that subset is the only part that's not in the neighborhoods.
May you talk to each other for a minute? If you have anything to say?
Yeah.
Then all the only units are outside.
So find it when you're outside.
Yeah, so
Yeah.
say anything except subsets in there.
In there.
So you can just take
Take
like
n
anything
to be,
above that.
okay, yeah, so you take n to be the point outside of the smallest distance between. Like for all the points, you can take the distance outside, take the distance from that to p, and take the one of the smallest.
Outside is fine.
Yeah, what I was thinking is, I don't know, all the,
What finite dimension?
I can see like a finite subset, like how do we know if you just like that, but I was here, I would sort of.
That works too.
So you just keep shrinking.
Like, given this, that was, what big N.
Okay, and who wants to say something? Anything? Why?
So I was thinking,
So let me first write out what we need to show. So I want to show that for all epsilon greater than 0, the existence of n such that n greater than n ensures that the distance with p sub n to p is less than epsilon. Okay.
I guess I was thinking, so we know that, yeah, all the finite, the many Pn, if we consider the Pn not in the neighborhood, if we take the largest index of that set, yeah, we know everything larger. If we take it, big N to be that largest N, then everything larger than that big N is.
Exactly.
Yeah.
Exactly. Very good. So you say, well, we want to show that we can find an n. So fix epsilon. We want the corresponding big N. Right? We want the corresponding big N. We know this thing is true. We know the epsilon neighborhood contains all but finitely many of the p sub n. Right? Call them p sub n1, p sub nk. And then, how can we find an n past which everybody lies inside? Well, just choose an n that's larger than these guys' indices, as Wyatt suggested. Right? So let capital N be the max of n1 through nk. Then n bigger than that ensures that p sub n is not one of those finite many guys, right? And so Pn lies in the epsilon neighborhood, lies in the epsilon neighborhood. Yeah.
How do we know that like the finite number of points outside are like in the same or like
We don't.
or
Are you saying like in order or something like that? Or these need not be. This n1 may be bigger than nk, but we just take the largest of them.
okay. Because then we're saying from like indexes 0 to n, they're all outside there. But is there not a scenario where like some points are in the epsilon ball, and then as you continue on indexing, maybe outside and then like return back in, and then wouldn't that say like from 0 to n, there are some points that aren't in that ball?
No, because remember we already chose the epsilon ball so that the only guys who are not in there are these Pn1 through Pnk, right?
Mm-hmm.
The only guys not in the epsilon ball are in here. So let's choose an n that excludes all these guys. Then we're forced to be inside here, right? It is true that you could have some sort of kooky sequence where it looks like you're converging, but then you sort of jump out, and it looks like you're converging, and then you jump out. But that jumping out has to decrease over time. Otherwise, there's not convergence, right? Right. So like, yeah, if you had some sequence that every order of every power of 10 jumped outside, well, that wouldn't converge, right? Those jumps, it has to be, that tendency has to be inexorable, right? Yeah. Yeah, but just logically speaking, think like this, right? We found all the guys who fail this.
Yeah.
Choose something that excludes them. Then you must succeed here. Okay. Okay. So these are basic properties of convergent sequences. let me think for 1 minute, because I was gonna go one direction, but I feel like it might be better for you guys to if we go a different direction. No, I'm just going to stick with that direction. Sorry. It's too late to change. Okay. Okay, so this was what we've been talking about are just like sequences in general metric spaces. But let me sort of switch gears and talk about sequences of complex numbers. Okay. So now we're in the complex, in the complex field. We've got the field structure, and as usual, we'll need something like convergence and arithmetic. Namely, we need something like the limit of the sum of sequences equals the sum of the limits. We'll need something like if you scale a sequence, then it's the same thing as scaling the limit of a sequence. So assume that Sn converges to S, Tn converges to T in the field. 3, we need something like the limit of a product of sequences equals the product of the limit. And then we also need something like the limit of 1 over convergent sequence is the same thing as 1 over the limit of that sequence. Okay. The first two, I think I'll leave to you guys as exercises. No, let me say it this way. Try as exercises. Okay, I think those are good practice for you guys. For the third one, so right. We want to show that given any epsilon, then we can find an n such that if we're past that n, then SNTN minus ST is smaller than epsilon. Right, that the distance, right, that the distance of SNTN from ST is smaller than epsilon. Right? In other words, the absolute value of the difference is smaller than epsilon. Okay. And for this one, we'll play the same trick that we played, and this is kind of the same proof that we did before. You remember we said, what we have control over is, we know that Sn goes to S, and we know that Tn goes to T, right? So what we have control over are these things, right? We have control over these things, and then we work them in, right? We play the, try to slide in the things that we want, right? So notice that Sn minus s times Tn minus t is the same thing as, that Sn Tn minus St is the same thing as Sn minus s times Tn minus t plus s Tn minus t plus t Sn minus s. Okay, so this is the observation that we made previously. Some sense I don't need to do this again, but I think it's a little bit illustrative. So we're trying to show that this thing goes to 0, right? We're trying to show that this thing goes to 0. And now notice that observe. This is just a constant times Tn minus t, right? This is just a constant times Sn minus s. We know each of those things goes to 0, right? And so by the second fact, whenever you have a convergent sequence multiplied by a constant, it's just a constant times the limit of the sequence. We know that each of those guys goes to 0, right? So by part 2, we know that the limit of s times Tn minus t is s times the limit of Tn minus t. So that's 0. Right? And similarly for t Sn minus s. Okay. So what's the point? The point is that, to show that Sn Tn minus St goes to 0, it suffices to show that this first term goes to 0. Right? We use the simple things that we've already proven before to just toss these terms out, right? These guys go to 0. We don't have to worry about them. Okay. Okay, everybody all right? Any questions? Okay. Yeah, Harrison.
When we're eliminating those two terms, we're using fact 1 over there, right?
Fact 2.
1 and 2.
And I guess, yeah, and 1 also, yeah. Yeah. Primarily, I think of this more as 2, but yeah, we're also using 1. Because we're saying that the limit of this sum is the sum of the limits. Yeah, absolutely. No, you're absolutely right. Okay, so let's prove that claim, right? That Sn minus s, Tn minus t goes to 0. Okay, so proof: given epsilon greater than 0, we want to find an n past which each of these guys, is smaller than the product is smaller than epsilon. Okay. We want well, we know that we can make each of these guys smaller than square root of epsilon, right? Each of these guys goes to 0, so we can make each of them smaller than the square root of epsilon, and then that's the end. Okay, so I'll do it right here. Choose n such that n bigger than n ensures that Sn minus s is smaller than the square root of epsilon. Choose n prime such that n bigger than n prime ensures Tn minus t is smaller than the square root of epsilon. Then, n bigger than the max of those guys implies that the product is smaller than epsilon. And so we have.
Sorry, I didn't understand why setting it to less than square root of epsilon or.
Yeah, so think like we're trying to show that we want to show that given epsilon, there's this n past which this thing minus 0 is smaller than epsilon, right? That's our goal, to find a good time, right? Like some sort of like onset time past which this condition is always satisfied. Well, for this to be smaller than epsilon is the same thing as saying that this is smaller than epsilon, because that 0 doesn't matter, and when you take the absolute value of a product, you get the product of the absolute values. Right? So we need to find an onset time past which this is smaller than epsilon. But as long as you show that each of these guys individually is smaller than the square root of epsilon, then their product will be smaller than epsilon. So that's what it. Yeah. Okay. Questions? Questions? One of the comments in the feedback was that that people maybe don't feel comfortable asking questions. Like I'm not sure how to change that. I mean, like, other than I say, be more comfortable asking questions. Like that doesn't help, I guess, right? Like, but in some sense, it's what I said the other day about shamelessness, right? You kind of have to, just be willing to throw out your ideas and not care too much if they're wrong or not, right? Like, don't care. There's that. I don't know if you've read the physicist Feynman's, memoirs, right? You guys know the physicist Feynman? Some of you do, right? There's one essay that's called, why do you care what other people think? Right? And that's kind of the attitude you want to have. Like, who cares about all these other yokels or these other people? Just like, I've got my own learning to take care of, and I want to ask this question, right? So like, they may know the answers. So what? Like maybe they'll look down on me. I don't care, right? You wanna have that kind of attitude, right? Because otherwise you're sort of like holding yourself back, right? Like at Princeton, everybody was smarter than I was. Everybody, right? It's like eventually if you let that bug you, then you're gonna be oppressed the whole time, basically. Right? You have to be like, who cares about, okay, they're all geniuses, so what? Like, I've got my own learning to take care of, right? And I want, I like this stuff, and I want to, in 15 years' time, in 20 years' time, we're not going to be in the same room anymore, right? Like, they're going to be all over the world, I'm going to be somewhere. What they know now and what they know in the future has zero to do with me, right? Absolutely nothing to do with your pursuit of knowledge, your individual pursuit of knowledge, right? So like, don't let other people's don't let concern over other people's opinions, stymie your own pursuit of knowledge.
It's 2:16.
Yeah, thank you. But my first question was just to establish if that clock really was an hour off. Now I know it is, so you don't have to tell me.
Oh wait, yeah, the time change happened.
Exactly.
Yeah.
Wait, you did?
Sunday, yeah. Lost an hour.
This week?
Your clock's all
Sunday
adjusted.
happened.
Your clock's all adjusted digitally, so you did not even notice. You don't have any analog clocks, is what I'm getting.
No, that explains a lot.
Because I was like, oh my gosh, why am I waking up at 9 in the morning? I've always gotten up. Yep.
Mhm.
Okay. What should we do? Okay, I think this last example is worth doing. So this last one, showing that the reciprocal, right, that taking the limit of a reciprocal is the reciprocal of the limit is worth doing. So let's show that one. Okay. So okay, so I want to show, as usual, that given any epsilon, basis of time, such that if you pass that time, then 1 over Sn minus 1 over S. Remember, the Sn converge to S. Is in the epsilon neighborhood of 0, right? In other words, the absolute value of this thing is smaller than epsilon. Okay, and remember what we have control over, right? We have control. We have Sn goes to S, right? So we want to work that into the thing that we're trying to control. Here's what we have control over. Here's what we want to control. And you notice that that this, of course, is the same thing as S minus Sn over Sns. Right. So there we've worked it in. Okay. So algebra does it for you. Okay, so here's like the scratch work. We want to work in Sn minus S, and we do so. Right? We do so. Okay. So then you say, okay, now so we want to show that there exists an n such that past this point, this thing is smaller than epsilon. Okay, so the way you want to think is like, well, Sn is going to tend to S, right? Sn is going to tend to S. So this thing on the bottom is roughly S squared, right? So as long as, so here's like the scratch work again, right? Sn over S, is basically, morally the same thing as S squared, right? So choose n such that past n, S minus Sn is smaller than S squared times epsilon. Right? Because if the bottom is basically S squared, and I can make the top like S squared times epsilon, then the whole thing is like epsilon. Okay? Okay, so now we need to make that reverse. Okay, so right, so Sn goes to S. So choose n. Choose n1 such that if we're past n1, then the size of Sn is bigger than 1/2 the size of S. Okay, this is my way of getting the size of Sn is roughly the size of S, right? It's bigger than 1/2 the size of S, and it's certainly less than this, I don't know actually, but it's bigger than 1/2 the size of S. Okay, I guess I can ensure that it's smaller than 3/2 the size of S, right? Because I can get it within 1/2 the distance. It doesn't matter. I'm just going to leave it this. Okay, let me not confuse you. Okay, this I hope you believe, right? I can get it so that it's within 1/2. It's bigger than 1/2 the size of S. Okay, so in that case, this 1 over SNS in absolute value, right? If I divide by something smaller, the thing just gets bigger, right? So I get 1 over 1/2 S squared. Right? In other words, 2 over the size of S squared. Right? So now what am I going to do at the top? Take 1 minute and finish the rest of the proof. I've handled the denominator. Now, with that control on the denominator, control the whole thing. Okay, turn to a neighbor and say, it is trivial. No. Okay, anybody want to tell me what I should write? Now, choose such that Harrison.
Okay, so now you can choose, what should we use for it? Let's call this epsilon 2. Epsilon 2 equals to epsilon, the epsilon we had above, equals to epsilon times absolute value S squared.
Epsilon so epsilon 2 is going to be
equals to epsilon
old epsilon
times the absolute value of S squared that all over 2.
Okay. Okay.
And then now you have a corresponding n2.
Mhm.
And now you pick the bigger among n1 and n2, and you have your n such that your above inequality holds.
Okay, great. So you say now, I'm just going to choose another n such that if you're past that n, then this thing is smaller than epsilon, this thing over 2.
Question. Is it Sn minus Sn or S minus Sn?
Sorry.
Great, thank you.
Okay, so that's true, right? Then for n bigger than either of them, we have that S minus Sn over SNS is smaller than, well, this thing on the top is smaller than epsilon over 2 absolute value of S squared, and then this thing on the rest of the term is smaller than this thing over S squared to cancel out and you get the epsilon. Okay.
This is.
Okay. I hope this is giving you some idea of the analytical way of thinking. Right? Like how do we think when we want to control these things? When we think, well, this Sn is basically S, right? This Sn is basically S. So, as long as you make a lot of sort of simplifying assumptions, and you say, this is basically this is basically this, and then it just all works out, right? And then you sort of then you have to tie down the details, right? But the first part is necessary as much as the second part, maybe even more necessary, because it shows how to do it, right? There's some it's like, oh, here's the strategy, and then now we need to execute the strategy. Okay, yeah, that's a bit less than I had intended to cover, but I think that's an okay place to stop. Hope everyone has a nice break.
I was just wondering, so I'm flying out tomorrow.
Okay.
Like,